levels from the operation of generation, transmission, and distribution equipment by entities subject to the Public Service Board jurisdiction. I am Jim Bowles, the chair of the Public Service Board. With me to my left is John Burke, a board member, and to my right is Margaret Cheney, another board member, and we have staff available as well. This workshop is being recorded by a court reporter, so when you speak, I ask that you identify yourself for the record and speak loudly so everyone can hear you. I think we had passed out an agenda, which we're going to follow today. The investigation goals are to examine whether the standard that the board has applied in previous cases is adequate to protect public health and safety and consistent with the best scientific information available today, and also to examine whether the board's current case-by-case approach to imposing sound limitations is appropriate to allow for the evolution of the standards based on the latest scientific information. I'd like to just describe a few rules of conduct for the participation of everyone here today. I'd like to urge everyone to stay within the scope of the investigation. I would note that we do have another public hearing event scheduled for May 7th, where people, I'm sorry, May 13th? May 13th at 7 o'clock.
Well, we do have one on the 7th, too.
We have a different one.
Yeah.
May 13th in Morrisville at the People's Academy. Thank you. So I'd really like people to stay focused today on the agenda items that we have and on the scope that I just described. We are striving to increase the understanding of the issues by the board and other participants. Participants should come to the workshop prepared to provide specific recommendations on the agenda items, agenda topics at hand. I'd urge only one person should speak at a time. No one should interrupt another person who's speaking. We have a court reporter, as I said, and she can only take down one person speaking at a time. Participants should be respectful to one another and avoid filibustering, in other words, extended comments, in order to allow everyone a fair chance to speak and to contribute. And each person should make every effort to stay on track with the agenda and to move the discussion forward. So I'm not expecting a problem, but I thought we would sort of remind everybody, because not all of you are regular participants in our process, remind everybody what are our general rules of the road here. I would just note that the investigation is not striving for consensus, although convergence of recommendations is desired if possible. We implement what we implement is pursuant to statute, and if we decide that the sound investigation suggests that there should be some changes to what we do, we may or may not be able to do that in the context of the orders that we've already laid out, or we might need to seek statutory changes. We'll have to see that. But what we want to do is hear from everybody and get a really fair airing of this issue, so that can help inform us as to how we should go forward in future cases. But we're not talking about any particular future case here today, because that wouldn't be appropriate. We're not permitted to have conversations about projects that may come before us unless they're properly noticed. And we haven't noticed anything like that. We've only noticed a general discussion. So the next item, I think the first thing we want to do is to hear from the presenter. We have people here today who are prepared to give presentations about sound. And so we've got people from the Department of Public Service, from Renewable Energy Vermont. We have a noise expert, Les Blomberg, and also Maureen Hessian, and we plan to hear from all of them today. As I understand it, the department has revised downward the request they had for who they wanted to present. Who's here from the department? Yes, Mr. Common.
Right, we have two presenters we'd like to put on today.
Okay. And how long will they be taking, do you think? My understanding was your whole presentation will be about 45 minutes?
Yes.
I'm trying to manage the amount of time we have, because we want to be sure we get through everybody and still have time for questions.
Yes, 45 minutes should do it. Absolutely.
Okay. And I understand Renewable Energy Vermont has a Mr. Bastash here, and he would like to be able to go first. Is that your understanding?
That was the agreement.
Okay, great. If you'd like to start, I think.
Okay, go ahead.
And if you could just give a little introduction about who you are, that would be very useful.
Certainly. So my name is Mark Bastash. I'm an acoustical engineer with CH2M Hill. I'm based out of Portland, Oregon. I've been working in the wind turbine sound and noise arena since the late 1990s. Contributed to a book on wind turbine noise that was recently published, and I'm a co-organizer with several others on the International Wind Turbine Noise Conference. I was going to start off with a brief introduction to sound, and then more or less kind of the basics of sound and some of the language and metrics that we use that will serve as the basis for some of my later discussion, as well as some of the other presenters, so that we'll only have one basic session. There's no test at the end of this. We're just going to try and introduce some of the terminology. If there's questions, I think we'll deal with them as you find
I
appropriate.
think we're going to try to hold questions until all the presenters are done, if that's acceptable.
Other than clarifying questions, if you don't understand something.
So what I'll start off with in terms of, and I'm hopeful everybody can hear me all right. I'm going to try and look at the slides as well as talk to the microphone. Basically, what is sound? Sound is a rapid pressure fluctuation above and below the static atmospheric pressure. It's expressed in a term called decibels. In terms of typical sound levels, 70 to 80 decibels is what we would encounter near a freeway or trains. Generally inside a building, we will see between 30 and 40 decibels given HVAC and refrigerators and other types of sounds that are in our daily lives. The typical audible sound range is from 20 hertz to 20,000 hertz. To put some of this into perspective for those who are somewhat musically inclined, the middle C of a piano is at 261 hertz. The lowest C on a piano is 33 hertz. There's a term called infrasound that is used to describe sound below 20 hertz. Another term that we use is low frequency, which overlaps a little bit the infrasound range and falls between generally 10 to 200 hertz. The threshold of hearing is higher for the lower frequencies. This includes infrasound, but all frequencies are audible if the level is high enough, and that also includes infrasound. For sound pressure level, when we're talking about atmospheric pressure and the fluctuations above and below it, the standard atmospheric pressure is 14.7 psi. For those of you who are divers, you might understand that in terms of 34 feet of water. When we are talking about a relatively loud sound, say 94 decibels, that's the OSHA occupational threshold for 4 hours. We're talking about a fluctuation of 0.004 inches of water. So the pressure fluctuations that our ears are sensitive to are very, very small. So there's not a lot of absolute energy there. The sound pressure level in the decibel was basically developed and described because we're dealing with things in a logarithmic scale, similar to the Richter scale or earthquake scale. We've got a very large range in relative energy that can span our audible range, and it would be very cumbersome for us to be talking about that in terms of energy. Therefore, this decibel criteria was, or decibel simplification was developed. And here is just a standard chart talking about general sound levels that we see in the environment. Decibel math is not very standard math. Can be very confusing. Even I work a lot with engineers, and it confuses quite a few of them as well. There are shortcuts or nomographs or slide rules that some people have developed. There's also some rules of thumb. But in acoustics, 50 plus 50 does not equal 53, or does not equal 100, it equals 53. And 50 plus 60 is equal to 60. So if two sounds are 10 decibels apart, they don't, there's no additive effect in the overall level. What's important to understand is if you're going to get into the details here, one must convert back to pressure before doing any of the math. and there's an example of how that's done. But there are some online calculators and other tools that folks can utilize. When we combine sources of the same sound level, there are some shortcuts that one can use. If you've got two sources of the same sound level, 50 plus 50 is equal to 53. If you've got 10 sources of the same sound level, we can add 10 to that sound level. So 50 plus 50 10 times is equal to 60. If you had 100 sources, it would be 50 plus 20, and that would be 70, and so on. So it's, again, a logarithmic math can be complicated and confusing.
Can I interrupt you for a second?
Sure.
When you switch slides, could you say that you're doing that so that that is reflected on the record? And so somebody reading the transcript? You're doing that, okay?
Right.
Okay, never mind. Okay, great.
Sound power level is another concept that we use in acoustics. Sound power level differs from sound pressure level. Sound power level is used in models. It's an accounting of the total acoustical energy that is irradiated or associated with the source. 1 watt of acoustical energy is equal to 120 decibels sound power, and 1/10 of a watt is equal to 110 decibels sound power. Overall, we're talking about very small quantities in terms of absolute energy. Sound power level is independent of distance from the source. It's similar to the wattage of a light bulb. The sound pressure level, what one hears or would measure directly, varies with distance or location. It's similar to the brightness or intensity of a light bulb. When we're talking about sound pressure levels, it's very helpful, and really we should always specify either the distance or location if we're characterizing a source. When we talk about sound power levels of equipment, we'll often see sound levels that are over 100, 110 decibels, and some industrial equipment will see sound power levels of 140. That, if you look back to that chart where we had sound pressure levels, that would say it was a jet taking off from a carrier. It's important to understand that power and pressure are different, and we can't really compare apples to oranges. That's the primary purpose of pointing this out.
If I might interrupt you again, we had a misunderstanding up here. I would like you to say which slide you're on as you go to each slide so that the reporter will take down that statement of yours, and someone reading the transcript will be able to follow along with the slides by seeing when you're changing the slides.
Okay, so just state the slide number.
Yeah, exactly.
Okay.
So now you're on
so
slide
we're on
8.
slide 8.
Right.
Thank you. So we'll move to slide 9.
Great, thank you.
Thank you. So again, to reiterate, though interrelated, the sound power and sound pressure levels cannot be directly compared. Sound power level takes into consideration the size of the source. The sound pressure level of a pump, say a 5 horsepower pump and a 500 horsepower pump, will be the same. 85 dBA at 3 feet is a common specification given OSHA limits, but the sound power level will be dramatically different because the 500 horsepower pump is larger. Again, the main point here is power and pressure can't be intermixed. They're different quantities. So next slide will be slide 10. Then I'll try to introduce the concept here of our threshold of hearing. Sorry, the title of the slide needs to be corrected. This is more on the fundamentals of perception. What we're showing here is curves of equal loudness. The dotted line represents more or less the hearing threshold, and there can be deviations in hearing thresholds between individuals, and our hearing thresholds change over time. But these are some standardized plots of this. What this shows is that in the lower frequencies, the threshold of hearing or our audible range is compressed, and the threshold of hearing is higher for lower frequencies. Again, all frequencies are audible if the sound is high enough, and that's true even as we extend further to the left, but that's not shown here. And as a concept, 30 decibels at 1,000 hertz, which will be here, is equally as loud as 65 decibels at 40 hertz. So we're just moving up this curve of equal loudness. So loudness has to do with how our ear and our hearing system responds, perceives the sound, and it's different for different frequencies. Again, middle C of the piano is around 260 hertz. Lowest C of the piano is 33 hertz. So we can move on to the next slide, 11. In the field of acoustics, we've developed several weighting systems, A weighting being one of them, C weighting being another. The B weighting has kind of fallen out of favor. The A weighting generally represents the inverse of the 40 foam curve. It's developed for moderate sounds. The C weighting really represents one of the higher curves in terms of its overall shape. They're kind of inversed there or flipped, and was originally intended for more industrial acoustics or industrial sounds. Low levels of sound are audible if the frequency varies from the background level. So if you have an overall level of, say, 40 dBA, but you introduce another low level of a bird chirping or of a motor humming, you can still hear it. Just because it's same or similar sound level doesn't necessarily mean it's going to be fully masked. Masking is a much more complex phenomenon. And we'll move to the next slide, 11. With regards to wind turbines, the sound generating mechanisms are primarily aerodynamic. The trailing edge of the turbine is noted to be the most important. The sound is generally proportional to the tip speed to the fifth power. There are many complex mechanisms at work in aeroacoustics. Our typical noise control solutions that we use for other types of industry are not applicable. We can't put barriers around the turbines. We can't enclose the turbines or the blades themselves because that is contrary to letting the wind allow them to operate. They spend a lot of time and effort in designing the airfoil, and any changes to anything that changes the shape of the airfoil ultimately will influence the character of the sound. Next slide is 13. This is a demonstration or a research project that was carried out in the Netherlands in 2007. This is one could call this acoustic holography. This is just showing the primary source of the sound being the trailing edge of the blade as it passes more or less the 3 o'clock position. Next slide, 14. Mechanical sound in wind turbines include the generator, the gearbox, yaw drives, cooling fans. Within this part of a wind turbine, standard noise control measures are used: vibration isolation, acoustical blankets, acoustical silencers. So we have seen a lot of treatment go into the nacelles over the last 10 years, so we're not seeing, generally speaking, lots of nacelle noise, and aerodynamic noise tends to be the most. It still requires vendors to pay attention to what's going on in the nacelle, and when they do, we see the aerodynamic noise being the dominant source. Next slide. With regards to sound propagation and modeling, when is modeling required? Well, it will depend on how close the compliance points are, how close are noise-sensitive areas, how many turbines there are, what types of models are generally used. Most models are based on ISO 9613 Part 2. This is the international standard for sound propagation outdoors. It's been included into a number of commercial packages, SoundPlan, CADNA, some wind turbine-specific ones as well. There are a number of other approaches that are available as well. They all generally use and are based on the turbine vendor sound power level data that is computed and used or derived according to another international standard, the 61400-11 standard. That's a standardized method used around the world to quantify the sound rating. That looks at it in terms of when we do the models, we generally want to be looking at both near cut-in speeds as well as the sound level or the maximum sound level that the turbine will generate. There is a lengthy discussion that goes on for about 40 pages or so in a book, the Wind Turbine Noise book by Andrew Bullimore and Fowler and Leventhal, so I won't go too much into detail into all the variations, but there is quite a wealth of literature on this topic if folks are interested. Slide 16. what are our primary noise attenuation characteristics? Well, distance is our primary attenuation characteristic. Distance attenuates more or less at 6 decibels per doubling a distance from a single source. When you've got an array of point sources or a line source such as a highway or road, we're generally looking at 3 dB per doubling a distance. Next slide is 17. We can get topographic effects depending on the source and the configuration. When topography completely blocks the line of sight and does so sufficiently, you can get topography acting as a barrier. Barrier attenuation typically will vary between 5 to 20 decibels. It will depend on the magnitude of the barrier and the level of shielding. Barrier effects can be diminished by a number of factors, including downward refraction. The UK Institute of Acoustics has developed some guidance, and there's some other guidance out there specific to addressing topographic shielding for wind turbines. Next slide is 18. Other sources of attenuation are atmospheric or molecular absorption. This becomes a more significant quantity as we move further away from the source. As you move beyond out to 1 kilometer or 3,000 feet, at the higher frequencies, you will see an 8 decibel attenuation just due to molecular absorption. At the lower end, say 250 hertz, you'll only see a 1 dB attenuation. Somewhat one reason why you can perhaps hear a train for some distance is that the high frequencies get knocked out, but the low frequencies do not. We then use our engineering models to evaluate in this case, a wind turbine sound level characteristics. Our engineering methods, ISO 9613 in particular, have been shown to predict A-weighted sound levels reasonably well. There's been a number of studies that look at this. And they, when specified or used appropriately, they could be considered as the basis of regulation. And I'll just point out here in this graph, so what we're talking about here is this is what was predicted from a turbine sound level, and this is the scatter around individual measurements that they collected. These levels vary between 30 and 40 decibels, sometimes a little bit beyond. Then what these researchers did is they went back through, isolated the periods where things would be caused by other sources of noise, and they show that they're when they use their model, they're generally falling within their predictions. And then next slide will be 20. So with wind, our mitigation options tend to be limited. These are 2 power plants that I've worked on, one in Australia, one down in New York. Both had sound guarantees. When we look at wind, or when we look at a conventional power facility, we can put things in enclosures. We can add silencing. A lot of those options aren't available to us when working on wind. The options available to us generally result in reduced power output from the wind turbine by slowing it down. And the only other point I'd bring out is moving beyond the A weighting as a criteria increases the uncertainty of predictions for all sources, not just wind, so that if we move beyond A weighted, we've got uncertainty to deal with for all types of different sources that affects conventional power as well as renewables. Next slide would be 21. Just very quickly, when we do the IEC testing, we do take measurements very close to the turbine at a hub height plus 1/2 of a rotor diameter away. That's because that's where the sound of the turbine will clearly be dominant, and we don't have to be concerned with other sources of sound. We'll go ahead and skip to the next slide, 22. When we're doing wind farm sound measurements, measuring close to the turbine is not the point of interest typically, and a ground board is not practicable for long-term measurements. We've got rain, we've got snow, we've got animals that can trample on it. So we have to develop a way to shield the microphone from wind. Measurements in windy environments are a challenge. It's a challenge that NASA first identified in the wind turbine range realm in the 1980s, and we still haven't figured it out completely. Still, there are some best practices that have been developed, but we don't necessarily have a uniform approach in the scientific literature developed yet. recommended practices are generally to use oversized or secondary windscreens. This is the test I conducted with others to help support an ANSI effort on evaluating of windscreen performance. We generally do recommend looking at collecting ground level and hub height wind speeds. But again, it's important to realize that perfect solutions here are still elusive. Next slide. Again, part of the challenge we have is dealing with wind-induced noise. There's two real primary sources: wind across the microphone and that of rustling vegetation. Windscreens help reduce noise on the microphone. They're not entirely perfect at all frequencies at all times. There's also the natural variability in ambient sounds. This is true particularly in a windy environment. We are able to conduct testing of other power facilities when the winds are calm, so we can remove that equation. We generally have a challenge doing that with wind turbine facilities because they generally need the wind to operate. I'll go ahead and we can skip to the next slide, 24. Wind shear is a factor that one needs to at least be aware of, if not take into account. Wind shear is a phenomenon which deals with the variation of wind speed at height. Wind speed can change with height, and the ratio of a ground level wind speed to a hub height wind speed can vary both diurnally as well as seasonally. The main point I think I'd like to convey here is that when looking at predictions, it's very good and useful to at least have evaluated the project and a prediction when the turbines are operating at their rated maximum sound power. That way, regardless of wind shear, you have calculated the maximum, or the calculated maximum of the turbine. Next slide. Talking a little bit about regulations in the U.S., according to a 1990 survey, which I think was conducted by one of the gentlemen in the first row, only 13 states had regulations for any sources, not just wind turbines. 5 of the 13 had them on the books, but do not enforce them. What we're seeing now is, some states do not have regulations, but they have guidance, and sometimes the regulations are poorly worded or ambiguous. A lot of times, acoustical professionals are not necessarily brought in to draft the regulation, and it is a complicated field, and there's a lot of ways things can get confused in that regard. Move on to the next slide. So we develop regulations because we're trying to encourage land use compatibility. Land use compatibility is a complicated subject. There are many factors that play into land use compatibility. Not all of them have to do with acoustics. There can be many others who are concerned with visual impacts, that are concerned with historic tensions between rural and urban areas. There's been some sociological studies in Australia and elsewhere that point to this. The next slide, 27. Wind turbines are not unique in eliciting strong objections from some. Airports are also a source of community noise that experience some strong objections. This is from a conference in the UK from Dr. Ian Fundell, the Institute of Sound and Vibration Research. Airports are recognized for their social benefit of providing opportunities for air travel. Airports are major employers, they're net economic contributors, and they also have a long history of noise management and public engagement. Next slide, please. Again, Dick Fowler from the same conference in the UK. We see many parallels perhaps between wind turbines and those of aircrafts. The benefits, the subsidies, the people not feeling like they're being treated, all these are parallel to those associated with the work that's been done in aircraft noise with regarding to personal benefits, with regards to perceived predictability and perceived control, as well as trust and recognition and fairness in the process. Next slide, 29. Again, as acoustics at the root of all community challenges, it will depend, and there are many moderators that come into that, but we try to address what we can through acoustic regulations. Next slide, 30. What are our general approaches for wind? We generally have, and this is perhaps for all sources, a absolute fixed sound level limit. 45 dBA would be an example. A relative increase or change, so 5 decibels above existing being an example. A combination of the two would be 40 decibels or 5 dB above existing, whichever is greater. And then you might include a ceiling, but not above 50, but not above 60. There's lots of ways those can be interplayed. Next slide is 31. When we're dealing with the relative criteria, we need to define what is our baseline. Increase over what? This is from a National Association of Regulatory Utilities Commissioner study that was done in 2011. This shows the scatter and pre-project measurements spans 10 to 15 decibels. There's a trend line that was drawn through that. But if you're at that trend line and you choose that as your basis, sometimes you're going to be over, sometimes you're going to be under. That is just a trend. Ambient is constantly changing. It's not very easy to necessarily pin down. So then you've got to assess, once you've decided how you're going to determine what your baseline is and how you're going to evaluate it, what is going to be an acceptable level of change? Is 15 decibels going to be okay if the resulting sound level is less than 45? How are you also going to deal with the natural temporal and spatial variability and probability that comes into play? We're dealing with environmental systems. Environmental systems do not behave necessarily very neatly like engineers would like them to. And then you also have to evaluate consistency with other sources. Are you going to treat wind differently from other sources? Next slide, 32. When we look at the federal policy for noise, it varies by agency. We've got the Federal Energy Regulatory Commission. They regulate based on a 55 LDN or DNL, a 24-hour average. We look at the Federal Highway Administration. They generally regulate on a peak hour basis of 67 LEQ or a substantial increase, which is generally 10 to 11 decibels. There's the FAA, EPA, HUD, all come up with their own guidance. There is not a single noise rule that governs everything in the United States.
What is DNL?
DNL is a 24-hour average that includes a 10 decibel nighttime penalty. This is an example of an allowable increase from the Federal Rail and Transit Administration. When the existing sound level is 40, they're saying there is no impact if the sound level is increased by 10 decibels, that there is an impact if it was increased by 15, so they'll allow you to go from 40 to 50 and say no impact. 40 to 55 would then be considered some sort of impact, and above that would be a severe impact. There's then a sliding scale as the existing levels go up, the allowed increase goes down. So that's just one approach that one agency has developed. Next slide. In Oregon had a noise rule on the books since the 1970s. It's the state I've got my professional engineering license in acoustics from. The standard for wind turbines is 10 decibel L50 or median increase above existing levels, or 36 dBA, whichever is highest, unless the neighbors or owners of a noise-sensitive dwelling agree to a higher level via noise easement. That's a legally binding document that's filed against the property. The maximum allowable level, regardless of noise waiver or noise easement, is 50 decibels. Another example on the next slide, at 35, is New Zealand, which went through a rather extensive rulemaking process and has a 15 or 20-page standard that you can purchase. They look at the greater of 40 decibels or 5 decibels above the existing level. They do identify restrictions for what they call as high amenity areas, but they more or less establish a floor and say the sound level shall not be not be less than 35 decibels there. They include penalties for what they call special audible characteristics tones or excessive amplitude modulations. And they found that addressing other characteristics such as infrasound or low frequency noise or gunborne reverberations were not justified in their review. Next slide, 36. Denmark has a calculation method that's similar to ISO 9613. They predict the A-weighted levels outdoors at 2 wind speeds. They then also calculate the interior sound level based on a typical or generic outdoor to indoor reduction for a typical dwelling of Danish construction. Compliance measurements at the dwelling are not required, but if there is a tone that's realized, there is a tone penalty. Next slide is slide 37. This is the Netherlands. The Netherlands, as we all know, is a relatively small country. They went through a rather long rulemaking process. The importance of renewable energy was acknowledged. They realized that their national goals for renewable energy could not be met with more restrictive limits, and policymakers decided on how to balance those two priorities. They went down a health-based guideline process based on the evaluation of Dutch and Swedish studies. They worked out a process where the wind turbine sounds are calculated on an annual average basis. They have established an annual limit of 47 dBA LDEN. That's similar to the LDN with the nighttime penalty. The Europeans add an evening penalty as well. And then they also have an average nighttime level. Again, these are average levels. These are not instantaneous levels that cannot be exceeded, never. These are average levels, and these are calculated based on a agreed-to calculation method based on actual wind statistics. Next slide, 38. In doing so, they realized that 8% of the population would potentially be highly annoyed indoors from wind turbines. They determined this to be similar to the percent annoyed from other sources, planes, trains, and automobiles, for example. Their process does not require far-field measurements at the residential locations. Modeling is done similar to the ISO 9613-2 standard. The annual average calculation considers the variability in wind speed and wind direction based on wind statistics. And they note that the average level of 41 dBA L night was considered consistent with their interpretation of the World Health Organization guidelines. Next slide, 39. They base their regulation on a dose-response relationship, with dose being sound level, response being annoyance or sleep disturbance. That was developed specifically from studies related to wind turbines. Because they used these studies that were specific for wind turbines, they said there's no need to specifically address these other characteristics because they were already part of the sample of those studies. Next slide, 40, I think. That was my time.
Great. Thank you.
Will you be here for questions after everybody's done?
Sir.
Okay, great. Get ready for the departments. Presenters. If you could identify yourself and just tell us a little bit about you.
Hi folks, my name is Payam Ashtiani. I'm a principal at Air Acoustics Engineering. We're an acoustic consultancy out of Toronto, Canada, and we're here to do a talk on behalf of the board on, the department, sorry about that, on issues of noise and power project. My specific presentation focuses on measurements of noise in an industrial or an environmental context. And so I'm going to be going through more of the measurement aspect and what the pitfalls and things are that people should be aware of. In the next slide. As I mentioned, well, this is a little about us. We're an acoustic consultancy. We're about 30 people, founded in the early 70s, and have been working on acoustics, noise, and vibration consultation issues for the past 4 years. In the context of, next slide. In the context of wind specifically, we've worked quite a bit with regulatory agencies, giving advice on appropriate measurement methodologies and conducting measurements post-construction as well as pre-construction. We've worked for developers in ensuring the layouts of wind farms are appropriate. We've also done post-construction measurements of wind farms, at last count over 10,000 hours of that. So we've got quite a bit of experience in doing wind turbine noise measurements, and we've also worked for residents and people concerned about the effects of noise at their properties. Next slide. So let's get started. First thing to talk about is instrumentation and really what is a sound level meter, what is an appropriate instrument to do noise measurements. Essentially there are 4 classes ranging from class 0 to class 3, where class 0 is the most stringent, most accurate of the instruments, and class 3 is the equivalent of something you would buy to get just a ballpark reading of where noise levels lie, similar to the app on your phone or just an inexpensive noise meter. Class 1 and class 2 are the instruments that most consultants will use, and most noise professionals will use when taking outdoor noise measurements. Class 2 is typically for less sensitive situations where microphones and sound level meters become more robust in being able to withstand environmental conditions. Whereas class 1 is used for more accurate instrumentation that has lower noise floor and better linearity, but tends to be a little bit more sensitive to the environmental conditions. Our recommendation has always been to use class 1 when it comes to wind turbines, just because of the level of accuracy that is often required and often demanded. So it's always good to have as robust and as accurate as you can pieces of equipment taking noise measurements. In terms of the microphone, there's 2 types of microphones predominantly. There's free field microphones and random incident. Free field microphones are designed to be pointed at the noise source, and they're fairly directional, whereas random incident diffuse field microphones are meant to evaluate sound coming from all directions in an omnidirectional fashion. The frequency range of a microphone is also very important, and it depends on what one's trying to get out of the noise measurement. If you're interested in the sound in the audible frequency range, then you have to make sure that the microphone has that range. If you're worried about infrasound and you want to capture that, you have to ensure that the microphone is capable of taking noise measurements with a low enough noise flow for those frequency ranges. And if you want to take measurements that span all of them, you can get microphones that will do all of it. It's just at a cost, and that's really where things get complicated. The other distinction we should make is integrating versus non-integrating sound level meters. And the difference between these two, a non-integrating sound level meter is the equivalent of having just a dB scale that will fluctuate as the sound level changes, whereas an integrating sound level meter will be able to take the acoustic energy over a given interval, say a minute or 10 minutes or an hour, and get the equivalent sound energy within that time period. Next slide, please. So from a basic standpoint, in terms of context of measurements, there's really, from an environmental standpoint, 2 scenarios where noise measurements will be taken. Near field measurements, where you're close to a specific noise source, where you're trying to quantify the sound emission from the source. As Mark was saying, you're trying to quantify the sound power of the source to get an idea of how much acoustic energy it emits. In those situations, you're usually close to the source. You have a high signal to noise ratio. And what I mean by that is that the signal, which is the thing that you want to measure and quantify, is much louder than your background noise that's contaminating that measured level. So you have a high signal to noise ratio when you're near field. And again, that's for sound power. Once you get to where people live and where people receive that sound, that becomes the far field measurement. And there, really, you're trying to quantify the cumulative noise at a given point. And you're trying to, in most situations, verify or validate your model and just try to see if the noise level that you expect is in fact that which is occurring. You usually have poorer signal-to-noise ratios, so you have to be very careful in making sure that you minimize the contamination from ambient or sources of noise not being the ones you want to measure. Next slide, please.
Yeah.
Other factors to consider. So, the other things that would affect measurements and their validity, in the first sense, is the temperature of the environment when those measurements were taken. The microphone, the sound level meter, the preamp, they all have ranges of temperatures for which they're valid, and different mics will have different ranges depending on, again, what level of instrumentation you have. But that really is important to ensure that the measurements being reported actually fall within the measurement, the temperature range for which the instrument is okay. Humidity is another factor where during high humidity situations, water droplets can form on the actual diaphragm of the microphone, affecting the accuracy of the microphone again. There are microphone systems that will include desiccants and ways of reducing the impact, but that's definitely something to consider. The next bit is wind speeds, and in most environmental noise situations, the consultant or practitioner would prefer the least windy case that they can find, just to minimize the noise contribution from the wind itself, whether it's the ambient reacting to the wind, or whether it's the airflow over the microphone causing turbulence and a false signal. If you want to imagine when you have a phone conversation, if somebody blows into the telephone, you hear the kind of shushing sound on the other side. It's not an actual sound. It's just the turbulent air going over that microphone, and that microphone reacting to it. So really, if you want to be confident in the sound measurement reflecting the actual acoustic energy in the environment, you want to minimize that. You can do that with windscreens, but for wind farms and wind power projects, you have an issue because you want generally to measure when it's windy. And so extra steps are highly recommended. As Mark mentioned earlier, the use of ground boards is one way, larger or secondary wind speeds are another, as long as there's some consideration being given to the fact that the wind does affect the measurements. The other two are precipitation and reflecting surfaces. Precipitation, obviously, if it's raining, you're going to be measuring rain noise and not environmental noise from the sources that you want. So that's number one. And keep in mind that your equipment, if it gets wet, then it's more than likely out of spec. The other one is reflecting surfaces. It's an interesting one because in most situations, the goal of outdoor noise measurements is to quantify the sound that's coming in the free field. What happens when you get very close to a reflecting surface is that reflections from either the source you're trying to measure or other ambient sources can reflect off of the surface and be strong enough to start to affect the actual measurement, really, that's something you want to avoid as well. Next slide, please. So some typical sources. So a transformer substation is a typical source that's likely exists here in Vermont, and people have probably measured them. For transformer substations, when you're looking at the near field component, again, that's to try and quantify the sound power. There are standards that one can follow. This one good one is, for example, the IEEE standard on the slide, where the measurement locations are identified, and you basically measure around the source and try to quantify the sound envelope around the source and quantify the sound power by integrating the sound pressure over that enveloping surface. Far field measurements can also happen at varying distances from the transformer to ensure that the signal to noise is adequate, and you start to see some propagation effects. You can use that to verify a model, or if you're close enough to back calculate the sound power, ensure that the unit is performing to the specification. One aspect of transformer substations is that they're tonal. They have an audible tone. And just to give you a quick description of a tone, that's a tone. When you whistle, you make a tone. Everybody should, I think, be able to understand that concept. And most people agree that tones are inherently more annoying than broadband swishing noises. And so tones become important, and measuring and quantifying them also becomes important, whether it is a subjective or objective measure. There are subjective ways to measure tones where jurisdictions will have a practitioner assess whether a tone does or does not exist, and that will incur whatever the regulations say. And there are objective measures as well, where there's a sound level measurement, and that can vary in spectral resolution, but it's not left up to the subjective opinion of a practitioner on whether or not the tone exists, and if so, if there's a penalty and how much that penalty should be. Next. So the wind turbines themselves, that's the focus of most of the discussions today. So I'll jump right into the issues for wind turbines as a source when it comes to measuring them. Essentially, we've got a fluctuating noise source, which fluctuates depending on the wind speed, which fluctuates depending on the wind direction. And the character of the noise contains both a broadband component, which is the swishing noise of the blades, as well as various mechanical components, which could include the gearboxes and generators that are up in the nacelle, or equipment that's at the base, be it more fans or transformers or what have you. The measurements of challenges that you'd have to deal with, as Mark mentioned, is first of all, you're measuring in windy conditions. So the self-noise of your measurement system becomes very important. Being able to have a good handle on what is the self-noise of your system, and what is that related to, and how much is that affecting the overall number you're getting becomes very, very important. Again, you could do this with either double windscreens or trying ground boards or just large windscreens. But what's most important is that you know what that self-noise is. So when the levels show a certain number, you have an idea of how much is that is real acoustic noise, and how much is that is just pseudo noise that your microphone is reading out. You're usually in low signal to noise conditions. You usually have a fluctuating ambient, and the fluctuation of the source itself is based on the hub height meteorological conditions. So your ambient's fluctuating based on local conditions, and the noise source that's emitting is fluctuating based on, whether it's a windy afternoon and then maybe dies down in the evening and then it picks up in the morning. So the sound output is not constant like other sources. Next, please. So near field measurements are done to the IEC 614-11 standard. This is basically to ensure that the sound emissions of a turbine are measured consistently, and that they're reported accurately. The measurements involve putting a ground plane on and doing attendant measurements with the turbines both on and off, and with the turbine at different wind speeds, and taking 10-second snippets of average sound level data, and looking at the difference between on and off. The next, it's a little picture, yeah. So that picture shows the typical measurement, where here you see these are measurements with the turbine on, these two different data sets, and the orange one is the background for measurements taken while the turbine was running. And with this information, you can calculate the sound power level, and the accuracy for a typical case is plus or minus about 1 dB, depending on the variation in the turbine. Next slide, please. Receptor measurements can be very tricky. So, by receptor, of course, we mean where people live. And the issue here is that when you're far away from the project and you're close to where people are, typically you've got a very poor signal-to-noise ratio. And you now mix all of the other things we were speaking about into that. And so our recommendations have always been to only do nighttime measurements, because that's really when your ambient is the lowest. You've got the fewest flora and fauna type noises. There's a lot of diurnal insects or birds that'll be there during the daytime, and also increased human activity. So you really want to take advantage of the lowest noise floor that you can find. The second is to do measurements of the meteorological conditions, both at the measurement site and to know what's going on at the turbine hub. Because at the turbine hub is where the blades are, and the conditions there will determine how much noise they actually output. So you really want to have that information there. The other one is turbine on and off measurements. So the fact that you're doing measurements in a windy situation means that you have to deal with the ambient condition and the ambient quantification one way or another. So it becomes very important to have both measurements with the turbines operational and to have measurements with the turbines parked or shut down temporarily. There are other options like using proxy measurement locations. They all have their pros and cons as well. So that's another thing to keep in mind. What is important from a data analysis point of view, the way you look at the data, ultimately what has to ensure that the sound levels that are reported are comparable to what the enforceable limits are. If the limits are in a specific metric, you want to be able to make sure that your measurements actually speak to that metric. And you also want to ensure that the sound levels that are being reported are actually quantifying the sound from the turbines. You also want to make sure that your intervals are steady state intervals, so that the wind speeds and directions not fluctuating wildly within one sample. So that to me means shorter intervals to try and isolate those varying conditions. And depending on the metric, that length gets factored in. I have a quick example here that LEQs, which are energy averages and prone to gusty and intermittent noises, should be kept to shorter intervals, like 1 minute, whereas if you take a statistical value like an L90, they should be more, they can be more longer term intervals. Next, please. The other thing you can do is look at statistical analysis, and this is really looking at having to deal with the fact that you have a fluctuating source and a fluctuating background, and the statistical analysis can look at how often a certain condition occurs. For example, in this graph we've got the x-axis being wind speed and the y-axis being sound level, increasing wind speed to the right, and the graph on the left is the measurements with turbine on, and the graph on the right is turbine off. And the dark spots, what they represent are higher probability occurrences. So the darker the spot is, compared to the other sound levels of that wind speed, the more often that condition occurred. So you can see that on the graph on the right, we have a constantly increasing level, but there is a spread around, this is reading around 34 dB here, 34 to 37. You can see that there is a spread around it, and there is some fluctuation, but a general trend is increasing, and increasing not quite linearly, but close to. Whereas the turbine on case, it starts off at similar levels as the turbine off, but then presumably once the turbines kick on, you get this added sound that happens at the different wind speed. Having had this information, here you go to the next slide. You could come up with the contribution probability of just the turbine by itself. So that would mean that we've now looked at just the turbine component, and now we can look at the probability and statistical distribution. So it no longer becomes, is the measurement of the turbines 43 or 44 or 46 or 40 or 50? We'll change the discussion to 95% of the time the sound level from the turbine component should be less than or equal to, let's say in this case, 47. And it makes it so that from a regulatory standpoint, it clears up a little bit of the confusion on why some measurements end up being inconclusive, and hopefully can give direction and enforceability from a statistical perspective. Next slide, please. The last thing I want to talk about very quickly is tonality. As I mentioned before, there's a couple of ways to do it, either subjective or objective. The pros and cons, there are pros and cons for both. From the subjective point of view, it's easy to administer because the practitioner says yay or nay. But there's a problem if there's two practitioners who don't agree on whether something's tonal. From an objective point of view, it's clear whether something is tonal and how tonal it is, how prominently tonal it is. But the downside is it's not always as easy. You need more detailed measurements, more detailed analysis. So those are the things to consider. Next slide. And I'm done. Thank you. Thank you.
Take care of that, right?
This is yours.
This is me.
Go ahead.
Yes. Thank you very much for inviting our contribution to your workshop. I'm here on behalf of the Public Service Department as well. And I'm going to be speaking about the acoustics associated with kind of the balance of energy facilities. Prior talks have